Welcome to part 2 on synchronous circuits. You may ask the following questions. What is a synchronous circuit? What are the rules for using flip-flops? And once we use these flip-flops, how do we initialize the outputs of these flip-flops so that we know what their outputs are in the first clock cycle? Okay, so we want to define what a synchronous circuit is. The building blocks are combinational gates, wires, nets, and flip-flops. And now we can build a directed graph that corresponds to a synchronous circuit, as we did in the case of combinational circuits. But if we do this, we may encounter cycles. For example, recall the sequential adder, where we had a full adder and a flip-flop, and the output of the flip-flop feeds the full adder. And we have this closed path, this cycle, in the sequential adder. So the directed graph, which would correspond to this circuit, would look like this. It would have a node that corresponds to the full adder, a node that corresponds to the flip-flop, and we would have a directed edge going from the full adder to the flip-flop, corresponds to the carry-out net, and then we would have a directed edge from the flip-flop back to the full adder, which would correspond to the carry-in bit. And now we have a directed graph with a cycle. How do we get along with this creature? Okay, now recall that a flip-flop has two inputs, the data input and the clock input, and these two inputs play different roles, and we have to make sure that we know what input port is connected to what in our graph, because you cannot connect a clock to anything you want, and you cannot connect anything you want to a clock input of a flip-flop. Okay, so the definition that we propose is based on a reduction to a combinational circuit. Okay, so here's the definition. We say that a circuit C is a synchronous circuit if it's composed of combinational gates, wires, and flip-flops, and it satisfies the following three conditions. Okay, first of all, we have a net which is fed by the clock signal, and this net is fed by an input gate, actually, which is giving the clock signal. Now, the set of ports that are fed by the clock net equals exactly the set of clock inputs of flip-flops. Okay, so this is our clock input, this is our clock network, and this clock network feeds exactly all the clock inputs of flip-flops. This is what you do with your clock network. This thing and only this thing. You do not feed the clock signal to any AND gate, OR gate, XOR gate, etc. You feed it only to the clock inputs of the flip-flops, and every clock input of a flip-flop is fed by your clock network. Okay, so these are the first 2 points. The third point is we employ a transformation that takes the circuit C and gives us the circuit C prime. We call this transformation stripping the flip-flops away. And then I'll define what this transformation is in a second. Once we derive C prime from C, we check C prime and we see that C prime is a combinational circuit. Okay, this is the reduction that I was talking about. Okay, so what is stripping flip-flops away? It's a transformation in which you start with a circuit C, which is a synchronous circuit, or a candidate. It's more a candidate for a synchronous circuit, and you want to check this circuit C. So what you do is you delete the input gate that feeds the clock and all the wires carrying the clock signal. So in effect, you erase the clock network. You remove all the flip-flops, and you replace every D port with an output gate and every Q port with an input gate. Let's see an example. Here's my circuit C, and this is the circuit C prime, which I obtained by stripping away the flip-flops. So you see in C I have two flip-flops and I have a clock network. So I remove the clock network, I remove the flip-flops, and I replace every flip-flop with an input gate and an output gate. This is the D port of the flip-flop. So here I'll have an input that corresponds to the D port. This is the Q port of the flip-flop. Here I'll have an output which corresponds, sorry, this is an output, this is an input, this is an output, this is an input that correspond to the D and Q ports respectively. I do the same thing with the other flip-flop, and now I get my C prime. So in C prime, all the original inputs, I keep them without a change. All the original outputs I keep without a change. All the combinational gates are kept without a change. All the nets that are not involved with the clock are kept without a change. The clock network is erased. Every flip-flop is removed and replaced with an output gate and an input gate. Now, I look at this circuit C prime and I ask myself, is this circuit C prime, is it a combinational circuit? And recall that the rule for a combinational circuit is that the directed graph that corresponds to C prime has to be acyclic. Okay, so in this case we need to check that our directed graph is indeed acyclic. Okay, so the only edge which goes from the right to the left is this edge. So this edge is a dangerous edge. It may belong to a cycle. So we follow this edge and we end up over here and we cannot close the cycle. Okay, so C prime is acyclic and therefore C is a synchronous circuit. How complicated is it to check that a given circuit C is synchronous? You want to check whether it's synchronous? Well, you check the clock signal. You see that it is connected to all the clock terminals of flip-flops and only to them. You strip away the flip-flops, you obtain a circuit C prime, and you check if C prime is a combinational circuit. And that we already know how to do because we built the directed graph. We check whether this directed graph is acyclic by trying to sort the vertices of C prime in topological order. Okay. Now, as I marked before, in a synchronous circuit, we may have closed paths. So, but these closed paths do not survive the transformation of stripping away the flip-flops. So the claim is that every closed path in a synchronous circuit traverses at least one flip-flop. And indeed, if I look in the sequential ladder, then I see that this is the only closed path I have, and it traverses a flip-flop. Okay? Good. So why is this claim true? Well, assume for the sake of contradiction that I have a circuit in which I have a closed path that doesn't traverse any flip-flop. So the closed path that lacks flip-flops survives the transformation of stripping away the flip-flops. That means that the directed graph that corresponds to C prime, the circuit I obtain after having stripped away the flip-flops, will contain a closed path, and therefore it is not combinational, and therefore the original circuit is not synchronous. And that completes the proof. Okay. One of the main advantages of following the definition of synchronous circuits is that their functionality is well defined. Okay, so let's make a few assumptions to help us understand the functionality of a synchronous circuit. The first assumption is initialization. At this point, we will regard initialization as a magic thing. And what initialization tells us is that for every flip-flop, FFI, we have an initial value, a bit, that denotes the value that is output by the flip-flop in clock cycle 0. Okay? Now we have an input sequence. Let's say that our input is denoted by X. And we we have an input sequence, and let's focus on one input gate X in our circuit. And let's denote by in a time t of X to be the value that is fed by this input gate in clock cycle t. Okay, so these are the initializations, and these are the inputs that are fed by the external world. Okay, and I want to emphasize that initialization serves a crucial role in the induction basis, which is used in order to explain the fact that synchronous circuits behave in a well-defined manner. Okay, so the simulation algorithm accepts as input the circuit C, its initial state, namely the outputs of the flip-flops in the clock cycle 0, and the sequence of inputs which are fed by the input gates. And our goal is to tell you what is going to be output by the circuit in every clock cycle. Okay, so you can view the circuit as follows. You have flip-flops, they have outputs, we denote them by S. You have inputs, they feed the circuit with values which we denote by in. We have a combinational part of the circuit. This is what remains after we have stripped away the flip-flops. And the outputs of the combinational circuit feed either flip-flops or output gates of the circuit. Okay, we refer to the output of the flip-flops as S, the inputs of the flip-flops as NS. This is for state and this is for next state. We have the inputs and we have the outputs. Okay, now notice that these flip-flops here and here need not be distinct. I'm just perhaps copying them twice to emphasize that here I'm looking at the Q output of the flip-flops, and here I'm looking at the D inputs of the flip-flops. Okay, simulation proceeds as follows. From time t0 to, say, time t minus 1, I will simulate the circuit clock cycle by clock cycle. In the for t equals 0, I know what the outputs of the flip-flops are. This is because of the initialization. And I know what the input gates feed the combinational gates, the combinational subcircuit. The combinational subcircuit, I know what it outputs because of the simulation algorithm for combinational circuits. These outputs feed the flip-flops and the output gates. The inputs of the flip-flops become the outputs of the flip-flops in the next clock cycle, and therefore I can increment t and perform the simulation in clock cycle t plus 1. Okay? So the idea is I do the reduction from a synchronous circuit that contains a flip-flop to a combinational circuit which is fed by flip-flops and inputs. And then I just do the simulation of the combinational circuit cycle by cycle. I can rearrange a synchronous circuit. I can group all the flip-flops together. And then I will have two combinational subcircuits. The circuit that computes the output and the circuit that computes the inputs to the flip-flops. Now often it is hard to separate these two circuits as they are depicted over here, in which case I may need to duplicate the circuits so that I could talk about the circuit that computes the next state and the circuit that computes the output. These are the global inputs. These are the outputs of the flip-flops, which feed both the circuit that computes the next state and the circuit that computes the output. We denote this circuit which computes the output by lambda, and the circuit that computes the next state by delta. So, what I want to emphasize is that any synchronous circuit can be rearranged to look like this, to have three parts: the combinational part that computes the output, combinational part that computes the next state, and all the flip-flops. Now, I mentioned so far the issue of initialization as an assumption. We require that the outputs of every flip-flop be defined during the first clock cycle. How can you do that? How can you even define what the first clock cycle is? What is the state of a flip-flop after you turn a circuit on? It was disconnected from the power, now I turn it on. What is going to be the output of the flip-flops? It might be 0, it might be 1. I have very little influence over the initial output of a flip-flop. And that means that I cannot tell what the initial value that is output by the flip-flops is going to be. And if I cannot say that, how am I going to use it once I want to power on the device? Okay, so this is a serious problem, and in fact it doesn't have a solution. So we will propose a contrived solution. The contrived solution involves introducing a new signal, a new player in the game called the reset signal. The reset signal is 1 if we're talking about the first clock cycle, and 0 otherwise. Now, I want to emphasize here something in the definition. What happens if I set the reset signal to be 1, after the circuit has been working for an hour? Then what happens is that, in effect, I'm treating the clock cycle in which, again, the reset is set to 1 as clock cycle number 0. And from that point, I restart the whole induction of the simulation. Okay? Good. So I have a signal that marks the first clock cycle, and I can, in fact, restart this marking by setting the reset to 1. And then I'm counting again from clock cycle 0. Okay, but who generates the reset signal? How does a reset signal differ from the output of a flip-flop? I just said that upon power up, I cannot determine the output of a flip-flop. So how can I make sure that I have a reset that equals 1 only in the first cycle, and after that becomes 0? So you see, I have run into a vicious cycle in my argumentation, and in fact there's no solution to this problem within the digital abstraction. Okay, so what can we do? We can try to reduce the probability of the event in which we do not know what the output of a flip-flop is in the first clock cycle. Okay, so again, the first clock cycle is simply the clock cycle in which the reset equals 1, and we just want to have a very high probability that such an event occurs, that the reset is 1 and then goes down to 0 for a long time until the next time we want to perform a reset. That would be the first thing that we want to have with high probability. And the second thing we want to have is that after the reset, we can treat all the flip-flops as if they were initialized to some predetermined value of an output. Okay. In practice, there's no way to generate such a reset deterministically. So what we try to do is do this with high probability, and the way it's done is by a circuit which is called a reset controller, which actually is supposed to generate a proper reset signal, and it does so with very high probability. Now, here comes the funny part. What does the reset controller actually do? Well, oddly enough, a reset controller is usually constructed by cascading flip-flops. These are the same flip-flops that we're trying to initialize. So we're using flip-flops in order to create the reset signal, and this reset signal will help us make sure that the outputs of the other flip-flops are going to be, say, 0 in clock cycle 0. Okay? So there is a whole vicious cycle which is happening here, and the explanation of how the reset controller actually works is not within the digital abstraction. It's outside the scope of this course. Okay, so now we have a reset signal, and we have this flip-flop, and in clock cycle 0, the output here is unknown. Okay, so we do not know what Q0 is. Okay, Q0 is something that we have no idea or control over, because this is the first clock cycle, and in general, Q of t plus 1 equals d of t. So Q of 0 is supposed to be equal to d at time minus 1. There's no such thing as time minus 1. This was before the system was powered on. Okay, so we don't know what Q0 is, and we have to bypass this problem. So what we do is we use the reset signal. The reset signal is 1 in clock cycle 0. So it feeds this mux, and the mux selects this input, and this input is directed, in clock cycle 0, is directed to S. And let's say that the initial state is 0, it could be 1 or 0, whatever you want, and therefore S0 will equal 0, because the reset signal tells you to select this input and direct it out to here. Okay, so whenever you do a restart, the reset is 1, you set t to be 0, since the reset is 1, you define the time, the clock cycle to be clock cycle 0. You select this input in the mux, and S0 will be equal to the initial state, which we chose to be 0. Now, this is a very dirty trick, because when we think about it, we have here a mux, which is a combinational gate, one input of which is well defined, it's a 0. The other input is well defined, it's a reset. We hope that the reset is functioning properly, that it's 1 in clock cycle 0 and 0 afterwards. But this input might not be logical, because we cannot make any assumption about the value that is output by the flip-flop. This is a flip-flop, I wish to emphasize. The value that is output by the flip-flop in the clock cycle 0. We have no idea what it is. It could be non-logical. So here we're assuming that this mux has a very special character, that if the reset is 1, then the output will equal the initial state regardless of the value that is fed through the 0 terminal. It could be logical, non-logical, it could do whatever it wants. It doesn't influence the output of S. So this is a very special mux, okay? Very special mux. So S equals the initial state if select equals 1 regardless of value in 0 input. Okay, good. So now, having explained this reset thing, we can describe the functionality of a synchronous circuit in its canonic form. Okay, so for every clock cycle I, well, if I equals 0, then S0 is the initial state. This is guaranteed by this part that we talked about just now, that this will be S0. NSI will equal delta of NI and SI. NSI equals the function computed by this combinational circuit applied to the input and the state in clock cycle I. Out I equals lambda of NI and SI, because this combinational circuit computes a function of the input and the state, and it gives you the value of the output. Sorry. And the flip-flop itself, SI plus 1 equals NSI. This is the flip-flop. It samples NSI, and it outputs SI plus 1, which equals NSI. And this mux, in the subsequent clock cycle, chooses this input because the reset will be 0. Okay, so we have a well-defined functionality of the synchronous circuit in its canonic form. Let's go back to the sequential adder and introduce the reset. So in the sequential adder we had the full adder, we had the flip-flop, and now we put here in between this funny AND gate. And what this AND gate does is it's just a strange way of implementing the mux. If the reset is 1, then the output of the AND gate is 0, because this is a small inverter before the AND gate. So this fellow, you can think of it as an inverter, and this fellow, of course, is an AND gate. And if the reset is 0, then you feed here a 1 into the AND, and therefore the AND simply outputs what is input through this port. Okay? So this is a way of resetting Cn to be 0 in clock cycle 0. So when we look at a sequential adder with reset, we look at all the times in which the reset is set to 1. Every such time is a way of restarting the counting of time. So if the reset is 1, then we forget about the past and treat the clock cycle t as clock cycle 0. Okay, so now if I look at clock cycle I can define Ri to be the last time in which I saw a reset. So Ri is the maximum t, which is at most I, such that reset of t equals 1. Okay. Now, if the reset is 0 for every j which is less than or equal to I, then Ri is not well defined because this is an empty set, and the maximum of an empty set, well, what do we do with that? Okay. In which case the functionality is unspecified because we will lack the induction basis that tells us what happens in clock cycle 0. However, if Ri is well defined, namely this set is not empty and you can take the maximum over it, then the functionality of the sequential adder will be that the number that is represented by the bits of A starting in cycle Ri until time I, and the bits of B starting at cycle Ri until cycle I, will equal what is represented by the sum output, again starting from cycle Ri and ending in cycle I, mod 2 to the power of I minus Ri plus 1. So I minus Ri tells us how many clock cycles have elapsed since the last reset. Okay. In the third part, we will continue with the description of finite state machines.